Hi, this is Mrs. LaBarbara. This is Physics Chapter 10, Waves Intro, Video 5. Today's topic is describing waves. The objectives are: know the definition of crest, trough, compression, rarefaction, wavelength, and phase. These are the vocabularies to describe a wave. Be able to determine the wavelength of a transverse wave or longitudinal wave. Determine whether points are in phase or how many degrees out of phase they are. Select points with a specific phase difference. Be able to select and sketch waves with a specific phase difference. Describe a transverse wave. A transverse wave is a wave that a particle in the medium moves perpendicular to wave's direction of travel. Here shows a transverse wave going to the right, but a medium moving up and down, so perpendicular to the wave's travel. So in this wave, you can see the amplitude is from equilibrium, the middle, to the very top. That's represent amplitude. The new vocabulary, one is called crest. Crest is the highest point. Correspondingly, trough is the lowest point. What is the wavelength? Wavelength is a length of one cycle, from crest to crest, or from trough to trough, or from this point to that point, as long as it's a points corresponding to one cycle. That's the wavelength. Crest, trough is the lowest point, crest the highest point. Wavelength is the length of one cycle. Kind of corresponding quantity would be period. Period is time of one cycle, not length. Wavelength is the length of one cycle. Similarly, we can describe longitudinal wave. What's a longitudinal wave? So in a longitudinal wave, the particles of the medium moves parallel to the wave's direction. So here is a wave going from left to right, and the local particles would be moving from right to left or left to right. That's parallel to wave's direction. So in here, the new vocabularies, instead of crest and trough, we have compression and rarefaction. Compression is all the particles are compressed together. Over here you have high pressure, or you can see on the slinky, all the rings are compressed together. Rarefaction is when they are all stretched out. In the air, that means at that point is a low pressure points, and over here is high pressure points. The wavelength is the length of one wave. It could be from a compression to the compression, the corresponding points, or from rarefaction to another rarefaction. So here is a compression, most compressed part. Rarefaction, most stretched out part. Amplitude is the amount of pressure in the wave. And wavelength is the distance from one compression to the next compression, or from one rarefaction to the next rarefaction. It has to be the corresponding points. And remember, the period is the time from one compression to the next compression. Obviously, the other one is the frequency, is number of cycles per unit of time. So period and frequency have the same definition as periodic motion. Let's take a look at this example. This diagram shows three waves. You need to determine the amplitude and the wavelength of wave A, B, and C. Amplitude is from the middle to the highest point. So here is from lowest to highest point has 4 meters. That means each interval has 1 meter. So the amplitude for A would be 2 meters. The wavelength is very similar to the period. Wavelength is total length divided by number of cycles. Corresponding period is total time divided by number of cycles. So the total length for all the waves is 12 meters. For A, how many cycles? There are 4 cycles for A, so the wavelength for A is 3 meters. Wavelength of B, by the way, the amplitude for B is the same as A because they have the same highest point. The wavelength is total length divided by cycle. For B, cycle is just 1, so that's 12 meters. For C, amplitude is 1 meter, wavelength is 6 meters, because for C, you'll have exactly 2 cycles. Let's take a look at longitudinal example. So here is longitudinal wave to the right, through a uniform medium as shown below. Points A, B, C, D, and E represents positions of particles of the medium. Describe the motion of particle at point C. Because this is longitudinal wave, so the particle moves parallel to wave's motion. Here is wave's movement from left to right, so C is also from left to right and locally, moving locally, okay? Which 2 points represent wavelength? The wavelength is the length of one cycle. So here is A at end of compression. Here's the next corresponding point at end of compression is C. So length of A to C is one wavelength. In the diagram, the distance between A and B on a wave is 5 meters. What is the wavelength? Remember, wavelength is total length divided by number of cycles. Total length is 5 meters. Cycle is 1, 2, 2.5 cycles. So the total length is 2 meters. The next vocabulary is phase. What is phase? Phase on a wave represents position of that point, usually in degrees or radian. Let's take a look at this diagram. The phase of C in this case is pi over 4. How did I get pi over 4? So here is one wave. One wave you have learned in math is 360 degrees or 2 pi. So half of the wave has to be pi. A quarter of the wave has to be pi over 2. C is between 0 and a quarter of the wave. So that's why the phase of C is pi over 4. The phase of A, as I said, is pi over 2. The phase of D is pi plus pi over 4. And phase of B is pi plus pi over 2. The phase of C prime is 2 pi plus pi over 4. The phase of A prime is 2 pi plus pi over 2. So those are the phases, the positions of the wave. Next one, let's see what is in phase. In phase are points on a periodic wave that moves in the same direction and have the same displacement from their rest position. That means same up or same down. In phase points are 2 pi apart, or 1 wavelength or 2 wavelengths apart, or 360 degrees or 720 degrees. By the way, 720 is corresponding to 4 pi apart. So let's take a look, C and C prime. This are corresponding to wavelength, one wavelength, and these are in phase. They are both moving downward, and they have both the same displacement. Both are positive and have the same distance from equilibrium position. They are in phase. So besides C and C prime, we have A and A prime also are in phase. B and B prime in phase, D and D prime are also in phase. Because all these points are 2 pi apart, or 1 wavelength apart, called wavelength is lambda, 1 lambda apart, or 360 degrees apart. Next vocabulary is completely out of phase. Completely out of phase points on a periodic wave moves in the opposite direction and have the opposite displacement. Means one is positive, the other one is negative. And they are usually 180 degrees apart, or half of wavelength apart, or 1.5 wavelength apart, and so forth. Let's take a look at this diagram. Which 2 points are out of phase? A and B are out of phase because they have opposite displacement. A is moving down, B is moving up, and they are exactly 180 degrees apart, or pi apart. Another out of phase is B and A prime. They are also out of phase. A prime and B prime also out of phase. The other one is C and D. They have opposite displacement. C is moving down and D is moving up. Okay, they are out of phase. They are 180 degrees apart. Let's see, B and A prime we talked about. Let's do a couple of examples. So here are a wave has many points, so which are in phase points. In phase points corresponding to the same points. A and E are in phase points because they have the same displacement. Both are negative, maximum negative points, and they are moving in the same direction. Both are moving up. So A and E. And they are 2 wavelengths apart. So because A to here, that's 1 wavelength, from here to here, another wavelength, multiples of wavelength apart. B and F, on the other hand, they are not in phase. Why is that? Even though they have the same displacement, but F is moving downward and B is moving upward. Also, they are not the multiples wavelength apart. B and this point is 1 wavelength apart, but this and F are not 1 wavelength apart. Out of phase point, out of phase, completely out of phase. C and E are completely out of phase. Why is that? Because they are half a wavelength apart. Also, they have opposite displacement and moving in the opposite direction. C is moving down, E is moving up. On the other hand, B and G, they are not out of phase because even though they have the opposite displacement, but they are moving in the same direction. B is moving up, so is G. And they are not half a wavelength apart. Okay, another example. For each of the following diagrams, indicate which points are in phase and which points are out of phase. In phase point is C and F. Those are in phase points. C and F because they are 1 wavelength apart. Points that are completely out of phase is B and D. B and D are out of phase. Another is E and G are also out of phase because the displacement is 0, but you can see they are half a wavelength apart. So they are out of phase. Which point on the wave diagram is in phase with A? In phase with A means one wavelength. So D is the corresponding point. A and D corresponding to 1 cycle. So the answer is D. Another example, the diagram shows a parked police car with siren on top. The siren is producing a sound of a frequency 680 Hz, which travels first through A, then through B as shown. The speed of sound is 340 meters per second. So if the sound waves are in phase at A and B, the distance between the points has to be multiples of wavelength. So the only multiples of wavelength is 1. Okay, that's the only answer. Another example, the diagram below represents a periodic wave. Which point is 90 degrees out of phase? So we already know the whole wave is 360 degrees. Half a wave is 180 degrees. 90 degrees is a quarter of the wave. So the quarter from point P is B. So that is the point. That's it for today. Thanks for watching.